In 1943, the Spitfire became too fast for its own pilots. Not because they lacked skill, not because they panicked, because the aircraft itself turned violent at speed. Engineers tried everything sensible, and none of it worked. Then someone proposed something that sounded embarrassing to even discuss. 2 propellers, opposite directions, 1 shaft. The room didn't debate it. They dismissed it as amateur engineering, until the numbers came back. 400 miles per hour, then more, then still more, without loss of control. At 470 miles per hour, the Spitfire wasn't fighting its pilot anymore. It was obeying. What embarrassed the engineers wasn't the speed. It was realizing that the solution they mocked had exposed a flaw they never understood. And that flaw mattered far beyond one aircraft. By 1943, the Spitfire had already earned its place in history. It had survived the Battle of Britain. It had outclimbed and outturned aircraft that were supposed to be superior. And for years, pilots trusted it with their lives. But the war was changing. German fighters were getting faster, higher altitude, heavier armament. And Britain needed the Spitfire to do something it had never been designed to do: go much faster. The answer, on paper, was simple: more power. That power came from the Rolls-Royce Griffin engine, an enormous leap forward from the Merlin. At nearly 2,000 horsepower, it promised to push the Spitfire into a new class entirely. In test reports, the numbers were extraordinary. Speed projections well beyond 450 miles per hour. Climb rates that could dominate any interceptor in the sky. But the first pilots to fly Griffin-powered Spitfires didn't talk about speed. They talked about control. At moderate velocities, the aircraft behaved normally. But as the throttle advanced and airspeed climbed, something began to change. The Spitfire didn't feel unstable in the way damaged aircraft do. There was no warning buffet, no gradual loss of authority. Instead, it felt like the aircraft was being wrenched sideways by an invisible hand. The moment pilots pushed past certain speeds, the nose began to yaw and roll violently, not gently, not predictably. It was as if the aircraft itself was resisting being flown. Veteran pilots, men with hundreds of hours in combat, reported the same sensation. The faster the Spitfire went, the more strength it demanded just to keep it level. This wasn't fear, it was exhaustion. At combat speeds, pilots had to fight the controls with both hands and legs, not to maneuver, just to survive straight and level flight. And the problem only got worse. Engineers analyzed the data and saw the pattern immediately. The Griffin engine's immense torque was twisting the aircraft in the opposite direction of the propeller's rotation. At low speeds, this force could be countered. Pilots compensated instinctively with rudder and aileron. Muscle memory carried them through. But at high speed, aerodynamic forces amplified the torque dramatically. The faster the aircraft went, the more violent the reaction became. This created a deadly paradox. The Spitfire was most dangerous precisely where it was supposed to be most effective. The faster it flew, the closer it came to losing control. Engineers responded the way engineers always do, by trying to contain the problem. They enlarged control surfaces to give pilots more authority. They adjusted engine mounts to reduce the transfer of rotational force. They experimented with propeller blade angles, pitch settings, and balance adjustments. Every solution made sense, and every solution failed. Increasing control surfaces added drag and weight, robbing the aircraft of speed. Structural changes weakened the airframe. Propeller adjustments reduced efficiency without eliminating the underlying force. Some proposed simply limiting top speed. Others suggested intensive pilot training teach pilots to fight the torque harder, longer, better. But these were not real solutions. They were compromises. And the war did not reward compromise. By late 1943, the situation had become critical. Britain had already invested enormous resources into Griffin-powered Spitfires. Production lines were being prepared. Naval variants were planned for carrier operations. If the aircraft could not be controlled at high speed, the entire program risked collapse. More importantly, the Allies faced a growing threat. Intelligence reports suggested Germany was pushing toward faster, higher-performing fighters. Jet development was underway. High-altitude interceptors were improving rapidly. Air superiority would be decided by speed, and Britain's most famous fighter was being defeated by its own engine. This was the context in which one proposal emerged, not from desperation, not from recklessness, but from a quiet recognition that the problem itself had been misunderstood. Instead of trying to suppress torque, one engineer suggested something that felt almost insulting in its simplicity. If torque was the problem, why fight it at all? Why not cancel it? The proposal was deceptively straightforward. Two propellers, mounted on the same axis, spinning in opposite directions. The forward propeller would generate torque. The rear propeller would generate equal and opposite torque. In theory, the forces would cancel. In theory, the aircraft would stop fighting itself. But theory meant very little in that room. The response was immediate and dismissive. Too heavy, too complex, too many moving parts for a frontline fighter. Some called it amateur engineering. Others said it belonged on experimental aircraft, not machines meant for combat. The ministry didn't ask for refinements. They didn't request further study. They rejected it outright. And at the time, they had every reason to believe they were right, because adding complexity in wartime usually meant failure. But what none of them fully understood, not yet, was that the Griffin engine had revealed a deeper problem, one that affected not just the Spitfire, but every aircraft being pushed toward the edge of performance. And until that problem was solved, speed itself would remain an enemy. The proposal didn't fail because it lacked logic. It failed because it violated instinct. In wartime engineering, simplicity wasn't a preference. It was survival. Every additional gear, bearing, or shaft meant one more point of failure, one more reason an aircraft might be grounded instead of fighting. And Joseph Smith knew that better than most. At 42, he had already built a reputation that made people uneasy, not because he was incompetent, but because his designs rarely took the shortest path. Smith understood aerodynamics intuitively. He saw forces the way other engineers saw components, and his solutions often pushed manufacturing technology to its limits. That history worked against him now. When he presented the contra-rotating propeller concept, the room didn't hear innovation. They heard risk. Two propellers on one shaft meant a complex gearbox. A gearbox meant precision machining. Precision machining meant slower production. And slower production, in 1943, could cost lives. Senior engineers ran through the objections almost automatically. Weight was the first. The system would add nearly 200 pounds to the nose of the aircraft, exactly where the Spitfire could least afford it. Balance was the second. Changing the mass distribution forward would affect climb rate, turn response, and landing characteristics. Then came reliability. A single propeller fighter was already a mechanical compromise. Now Smith wanted to double the moving parts at the most stressed point on the airframe. If one gear failed, both propellers failed. If lubrication faltered, the entire system seized. This wasn't theory. These were problems engineers dealt with every day. Someone compared the design to a mechanical puzzle. Clever on a workbench, disastrous in combat. Others worried about maintenance. Frontline squadrons operated in mud, dust, salt air. Ground crews worked under fire, in the dark, with limited tools. A system that required exact timing and perfect balance might work in a test hangar, but on an airfield carved out of farmland, the answer was obvious. It wouldn't. And then there was the Navy. Carrier operations punished aircraft harder than anything on land. Arrestor landings, catapult launches, constant vibration. Naval engineers looked at Smith's drawings and saw a system begging to shake itself apart. Even those sympathetic to the idea hesitated, not because they doubted the physics, but because war punished elegance. The Ministry of Aircraft Production listened to all of it. They had schedules to meet, contracts already signed. Factories retooled around the Griffin engine. What they needed was a fix that could be bolted on, not rebuilt from scratch. Smith's proposal wasn't a modification. It was a fundamental change. So the verdict came quickly. Too complex, Too risky. Rejected. But rejection didn't end the discussion. Because the problem refused to go away, flight test reports kept arriving. Different pilots, different airframes, same result. The Griffin-powered Spitfire remained uncontrollable at the speeds it needed to reach. Torque wasn't a nuisance. It was a wall, and every conventional method failed to breach it. Smith returned to his office with the same data everyone else had seen. But he read it differently. Where others saw force to be resisted, he saw force to be redirected. Torque wasn't random. It was predictable, measurable. And if it was predictable, it could be countered not by strength, but by balance. The mathematics were straightforward. The engineering was not. A contra-rotating system would require a gearbox capable of splitting power precisely, 2 output shafts, 2 sets of bearings, timing that could not drift, not by a fraction. The tolerances were brutal. Each propeller would need to be balanced to within fractions of an ounce. Any asymmetry would introduce vibration worse than the original problem. Smith calculated the weight penalty again and again. Yes, it was heavy, but the efficiency gains were real. Cancel torque, and the aircraft no longer wastes energy fighting itself. Thrust increases. Control returns. On paper, the numbers worked. What Smith couldn't put on paper was confidence. Confidence that the system wouldn't vibrate itself to destruction. Confidence that wartime manufacturing could achieve the required precision. Confidence that pilots would trust it. He requested another meeting. This time, the room was different. Not engineers arguing theory, but officials calculating consequences. Millions of pounds already spent. Production timelines slipping. Pressure mounting from operational commands. The Griffin Spitfire wasn't a future concept. It was a commitment. Smith didn't argue aesthetics. He argued necessity. He explained that torque was not something training could overcome. That adding control authority only delayed failure. That speed limits defeated the purpose of the engine. He didn't promise perfection. He promised one thing only. If the system worked, the Spitfire would finally use all of the power it already had. The room remained skeptical. One official asked the question everyone was thinking. How long? 80. Our key. Smith didn't hesitate. 6 weeks to design and manufacture the gearbox. 4 weeks for propeller fabrication and balancing. A prototype ready for flight testing by early February. The timeline was aggressive, almost reckless. But so was the alternative, because if the Griffin Spitfire failed, there was no backup waiting. Silence followed. Smith understood what that silence meant. This wasn't approval. It was hesitation. And in war, hesitation was sometimes the only opening innovation ever received. Finally, a condition was set. 1 aircraft, 1 prototype, full testing. If it failed, if it delayed production, the project would be buried immediately. Smith accepted without protest, not because he was confident, but because there was no other path left. As he left the room, he understood the real risk. If the design failed, it wouldn't be remembered as a bold attempt. It would be remembered as proof that the ridicule had been justified, and the idea everyone had laughed at would become the reason Britain's most famous fighter never reached its potential. By early 1944, the idea that had once been laughed out of the room was no longer theoretical. It was sitting on the nose of a Spitfire. Inside a hangar at Boscombe Down, the modified Mark 21 looked almost familiar until you reached the front. Where a single propeller should have been, 2 massive assemblies now dominated the aircraft's silhouette. They were mounted on the same axis. They spun in opposite directions, and between them sat a gearbox unlike anything ever installed on a British fighter. Nearly 200 pounds of precision machined metal. Gears cut to tolerances usually reserved for clockmakers. Bearings balanced so finely that a difference of half an ounce could destroy the system. This was not an experiment designed for comfort. It was built because nothing else had worked. Smith's team had spent weeks working under relentless pressure. Every calculation was checked and rechecked. Every component was weighed, polished, measured, and measured again. There was no margin left. The forward propeller rotated clockwise at 1,825 revolutions per minute. The rear propeller turned counterclockwise at 1,475. On paper, the opposing forces canceled perfectly. In reality, no one knew what would happen once the aircraft left the ground. Ground tests offered limited reassurance. At idle and moderate power, the system behaved acceptably. Oil pressure remained stable. Gearbox temperatures stayed within limits. But vibration lingered, subtle, persistent, unsettling. Not enough to abort the test, enough to remind everyone that this machine was operating at the edge of what wartime engineering could achieve. On the morning of February 23, 1944, the weather offered no favors. Low clouds, gusty winds, cold air cutting across the airfield. Inside Hangar 7, the aircraft waited. Squadron leader Jeffrey Wellham approached it with the caution of a man who understood exactly what was at stake. At 24, he was already a veteran. He had flown combat missions over Britain, France, and Malta. He had survived aircraft damaged badly enough to end careers. But this was different. This wasn't enemy fire. This was an unproven idea. Wellham studied the nose of the aircraft longer than usual. The twin propellers looked wrong, not defective, but unfamiliar in a way that unsettled instinct. He knew the reputation of the man who designed them, and he knew how little tolerance the air had for theoretical confidence. The test profile was conservative. Climb to 8,000 feet. Level flight at varying power settings. Gradual increases in speed only if the aircraft remained controllable. No heroics, no pushing beyond limits. Smith stood near the port wing, silent. This flight represented 6 months of work. It also represented the risk of public failure. If the system tore itself apart, there would be no second chances. At NEO, Fempton AM, Wellham strapped in. The cockpit was familiar, but not quite the same. Additional gauges monitored gearbox, oil pressure, propeller pitch, and rotational balance. He ran through the checklist with deliberate care. Then he started the engine. The Griffin fired with its deep, powerful rumble, but the sound was altered. Instead of the rhythmic pulse of a single propeller, the contra-rotating system produced a layered harmonic that vibrated through the airframe. Not violent, not reassuring. Ground control cleared the aircraft for taxi. As Wellham advanced the throttle, something unexpected happened. The Spitfire tracked straight. There was no leftward pull, no instinctive need to correct with rudder. For the first time since the Griffin engine had been installed, the aircraft behaved as if it were finally at peace with itself. Takeoff came at 85 miles per hour, exactly as predicted. The aircraft lifted cleanly. No sudden roll, no struggle. In the tower, engineers exchanged glances. Torque, the problem that had haunted the program for months, appeared to be gone. As Wellham climbed, the aircraft remained stable. At low speeds, the handling felt almost elegant, precise, predictable. But as altitude increased, another issue revealed itself. The climb rate was disappointing. To maintain 2,000 feet per minute, Wellham had to push the throttle much harder than expected. The additional weight was making itself known. By 5,000 feet, he was using nearly full power to achieve performance that should have required far less. He radioed the issue calmly. Boscombe Control acknowledged and cleared him to level off at 6,000 feet. There, something remarkable happened. Despite the climb penalty, the Spitfire flew beautifully. At 300 miles per hour, the aircraft that had once tried to kill its pilot now felt stable and responsive. Wellham tested shallow turns, then steeper ones. The Spitfire responded cleanly, without the violent torque reactions that had plagued earlier flights. It felt smaller than it was, lighter. For the first time, the Griffin engine's power translated into control instead of chaos. Then Wellham advanced the throttle further. At 350 miles per hour, the aircraft remained calm. This was the speed range where previous Spitfires had become dangerous. Now, nothing happened. Encouraged but cautious, Wellham continued. At 370 miles per hour, everything changed. The aircraft began to shake. Not gently, violently. The vibrations surged through the airframe, blurring the instrument panel and making it difficult to focus. This wasn't turbulence. This wasn't control feedback. This was structural resonance. The twin propellers, perfectly balanced on the ground, were now interacting in ways no calculation had fully predicted. Their tip vortices collided. Their harmonic frequencies reinforced one another. Instead of canceling out, the forces multiplied. Wellham immediately reduced power. The shaking lessened, but did not disappear entirely. Boscombe control. Test 27, he reported. Severe vibration above 370. Returning to base immediately. The landing approach revealed another surprise. With power reduced, the Spitfire descended faster than expected. The altered aerodynamics and additional weight demanded constant throttle adjustments to maintain glide path. Wellham touched down after 43 minutes of flight. He taxied back in silence. On the ground, Smith saw the expression on the pilot's face before a single word was spoken. The flight had not ended in triumph. It had ended in uncertainty. Ground crews swarmed the aircraft, inspecting the propeller assembly for damage. Remarkably, nothing had failed catastrophically. The system had survived, but survival was not success. 2 hours later, an emergency meeting convened in the hangar. The aircraft stood behind them, its twin propellers now motionless, still imposing, still unsettling. Wellham delivered his report carefully. At low speed, the aircraft was exceptional. Torque elimination was complete. Takeoff and handling were superior to any Spitfire variant he had flown. Then came the verdict. Above 370 miles per hour, the vibrations were severe enough to risk structural failure. Climb performance was significantly degraded. The room absorbed the assessment in silence. Smith had solved the original problem and created a new one that might be even more dangerous. Months of work had produced an aircraft that performed brilliantly where it mattered least and failed where it mattered most. The irony was brutal. Chief engineers reviewed the data, searching for explanations. Ground tests had shown harmonic vibrations, but nothing approaching what the pilot experienced in flight. The difference lay in aerodynamic reality. At speed, the interaction between two rotating propellers created complex airflow patterns that static testing could not replicate. The mathematics had been sound. The physics had not been complete. Officials faced an uncomfortable choice. The contra-rotating system worked partially, but partial success was not enough in war. One voice in the room asked the question no one wanted to hear. Could the problem be solved in time, or had the critics been right all along? Smith stood quietly as the discussion unfolded. He knew how close this project was to being terminated. He also knew something else. The aircraft had not failed randomly. It had failed for a reason. And if that reason could be identified and corrected, the solution everyone had mocked might still succeed. But now, there was no confidence left to spend. Only one chance remained. The room did not erupt in argument. It went quiet. That silence was worse than shouting. Around the aircraft, engineers stared at data sheets that no longer mattered. The contra-rotating system had done what it promised and revealed what no one had wanted to see. The torque problem was gone, but in its place stood something far more frightening. Uncontrolled vibration at high speed was not a flaw that could be ignored. It was a warning. A fighter aircraft that shook itself apart at speed wasn't merely ineffective, it was lethal to its own pilot. The conclusion hovered in the air before anyone spoke it aloud. This project was one step away from cancellation. Senior officials had already seen too many experimental programs fail, brilliant ideas that worked in theory and collapsed in reality. Time, money, and lives had been wasted chasing elegance when war demanded reliability. This looked like another one of those stories. The Air Commodore present that day did not raise his voice. He didn't need to. He simply asked the question everyone had been avoiding. Can this be fixed? Well, Smith understood what was being asked. Not eventually. Not with unlimited time. Fixed quickly. Fixed decisively. Fixed without disrupting production schedules already under strain. The room waited for his answer. Smith did not respond immediately. Not because he lacked one, but because he understood the weight of saying it aloud. Yes meant committing the remaining credibility of the program. No meant watching his design die in the hangar behind them. He chose neither. Not without changes, he said carefully. The phrase landed poorly. Changes meant delays. Delays meant aircraft not reaching squadrons. And that meant something far beyond engineering failure. The Air Commodore pressed him. You've already had months. What makes you believe this is solvable now? I'd not. Smith didn't defend the past. He explained the present. The vibration wasn't random. It wasn't structural weakness. It wasn't manufacturing error. It was resonance. Two rotating systems interacting in real airflow had created harmonic frequencies that ground tests and wind tunnels could not predict. At certain speeds, those frequencies aligned perfectly, turning smooth rotation into violent oscillation. But that also meant something else. If resonance could be created, it could be shifted. Gear ratios controlled rotational speed. Blade geometry controlled airflow interaction. Change either, and the resonance moved. Change both, and it might disappear entirely from the aircraft's operating envelope. Smith pointed to the data. The vibration peak occurred consistently near the same speed band. That meant it wasn't chaos. It was a pattern. The skepticism in the room did not fade. One official asked the question that mattered most. How long? And quote, newer is dead. Smith answered without hesitation. 3 weeks. 3 weeks of redesigning blade geometry. 3 weeks of adjusting gearbox timing. 3 weeks of rebalancing every component by hand. Then another test. The response was immediate and brutal. 3 weeks was an eternity. Production pressures were mounting. The Griffin Spitfire was already late. Every additional delay increased the risk of losing air superiority. Some argued the program had already crossed the line of acceptable risk, that the original critics had been right. Better to accept speed limitations than gamble on further experimentation. The room began to divide, not along technical lines, but along philosophical ones. One side believed war was won by refinement, incremental improvement, proven systems. The other believed the enemy would not wait. Intelligence reports had grown increasingly troubling. German development programs were pushing faster aircraft, higher altitudes, radical designs. The future of air combat would not be decided by comfort. It would be decided by who mastered speed first. Jeffrey Wellham had remained silent until that moment. When he spoke, the room listened. He did not speak like an advocate. He spoke like a man who had nearly paid with his life. Below 370, he said. This aircraft is the best I've ever flown. Windshield. He described the handling, the absence of torque, the feeling of control at speeds that had previously terrified pilots. If the vibration can be eliminated, he continued, this aircraft will outperform anything currently in service. After, the Air Commodore looked at him carefully. And if it can't? Ice. Wellham did not hesitate. Then you should kill the program. Rees, WEF. That honesty carried weight. The room fell silent again. The decision was no longer abstract. This was no longer an engineer asking for indulgence. It was a test pilot asking for one last chance. The Air Commodore finally spoke. One more attempt, he said. Not a negotiation. A verdict. 3 weeks. 1 aircraft. 1 flight. If the vibration remained, the contra-rotating propeller program would end immediately. No further modifications. No appeals. Smith accepted the terms without argument. He understood the reality. This was not an extension. It was a countdown. The hangar emptied slowly that afternoon. As officials returned to London, Smith remained behind with his team. The aircraft sat motionless, stripped of glamour. In its current state, it was neither a success nor a failure. It was unresolved. Smith gathered his engineers. There was no room for optimism, only work. The solution would not come from a new concept. The concept had already proven itself. What remained was execution. They began by dismantling the propeller assemblies completely. Every blade, every gear, every bearing. They examined wear patterns, airflow marks, microscopic imbalances. What they found confirmed Smith's suspicion. The blade tips were the key. At high rotational speeds, the interaction between the forward and rear propeller vortices was amplifying pressure waves. Those waves aligned with the gearbox's natural frequencies. The system wasn't failing. It was singing at exactly the wrong pitch. Smith recalculated the rotational relationship. The original configuration maximized efficiency, but efficiency had placed resonance squarely within the aircraft's operational speed range. That had to change. He adjusted the gear ratios, not dramatically but precisely, enough to shift the harmonic frequencies away from critical speeds. Then came the blades. The aggressive twist near the tips increased thrust but also intensified vortex interaction. Smith softened the geometry. A more gradual transition. Less violent airflow interaction. The changes were subtle, invisible to anyone without intimate knowledge of propeller dynamics. But they mattered. Every blade was reshaped by hand. Every component rebalanced to tighter tolerances than before. This was not factory work. It was craftsmanship under pressure. Sleep became optional. Failure was not. By the end of the third week, the aircraft was reassembled. From a distance, it looked unchanged, but Smith knew better. The entire system now operated at different internal rhythms. Whether those rhythms would harmonize or collide could only be answered one way: in the air. On the eve of the test, Smith walked alone through the hangar. He ran his hand along the nose of the aircraft. This machine represented everything that had gone wrong and everything that might still go right. If the vibration remained, the story would end here. If it was gone, the laughter that had followed his idea would finally stop. The morning would decide which version of that story survived. March 18th, 1944. The sky over Boscombe Down was clear in a way that felt almost deliberate. Light winds. Stable air. No excuse. The aircraft stood on the apron exactly where it had been 3 weeks earlier. Same Spitfire. Same engine. Same idea. But internally, everything that mattered had changed. Smith's team had finished reassembly late the previous night. Every blade had been reshaped by hand. Every gear ratio recalculated, cut, and verified. Every component balanced to tolerances so tight that even the machinists had complained. This was no longer experimentation. It was a final statement. Jeffrey Wellham arrived early. He walked around the aircraft in silence, stopping at the nose longer than necessary. He had felt what this machine could do. He had also felt what it could do wrong. This flight would not be cautious. Caution had already failed. If the vibration returned, it would return clearly. And if it didn't, there would be no ambiguity left. The ground crew completed their checks. Oil temperature steady. Gearbox pressure nominal. No harmonic spikes during ground run. Smith listened, but he didn't relax. Ground tests had lied before. At precisely 10:15, Wellham climbed into the cockpit. The instrument panel was unchanged, but his attention wasn't. He memorized every gauge position, every needle movement. The Griffin engine started. The sound was still unfamiliar, but different. The layered harmonic created by the twin propellers was still there, but muted, controlled. As Wellham taxied, the aircraft tracked straight without effort. No vibration through the pedals. No tremor through the airframe. He advanced the throttle. Takeoff came faster than before. The aircraft lifted cleanly and immediately began climbing with authority. At 80% power, the climb rate held steady at 2,000 feet per minute. That alone told Smith more than any report could. The weight penalty was no longer dominating performance. Boscombe Control cleared the aircraft for test altitude. Wellham leveled at 10,000 feet and began the methodical work of probing the speed envelope. 300 miles per hour. The Spitfire felt solid, predictable. 350. Still nothing. No vibration. No control resistance. Wellham made gentle turns, then steeper ones. The aircraft responded smoothly. The torque that once haunted it, completely absent. In the tower, no one spoke. They were all waiting for the same number, 370. Wellham advanced the throttle slowly. The airspeed indicator crept upward. 365. 368. Nothing happened. No shaking. No warning. At 370, the point where the first test had nearly ended the program, the aircraft remained calm. Wellham held it there. Then he pushed further. 380, 390. The Spitfire accelerated cleanly, as if the problem had never existed. Boscombe Control, Test 27. Wellham radioed, his voice steady, passing 400 miles per hour. No adverse handling. Smith lowered the binoculars slightly. This was no longer a fluke. Wellham continued. At 4 to 10, the aircraft felt more stable than most fighters at half that speed. The absence of torque allowed precise control inputs even under heavy power. This was something new. Most aircraft became less forgiving as speed increased. This one became better. Wellham pushed into a shallow dive. The airspeed climbed rapidly, 430, 440. Still no vibration. He pulled out smoothly, the Spitfire responding without protest. The revised propeller geometry had not merely removed the resonance, it had transformed how power was translated into motion. The aircraft no longer fought itself. It obeyed. For the next 25 minutes, Wellham explored every corner of the flight envelope. High-speed turns, rapid throttle changes, steep climbs followed by controlled dives. Nothing broke. Nothing shook. Nothing resisted. The contra-rotating system that had once threatened to tear the aircraft apart now worked as if it had always belonged there. When Wellham finally turned back toward Boscombe Down, the outcome was no longer in doubt. The landing was uneventful. As the aircraft rolled to a stop, ground crews rushed forward, but not with the urgency of fear, with curiosity. Wellham shut down the engine and climbed out. He removed his helmet slowly, scanning the faces around him. Then he spoke. "This isn't just an improved Spitfire," he said. "This is the finest fighter aircraft I have ever flown." Witzard. The words landed with weight, not enthusiasm, not exaggeration, professional judgment. The Air Commodore stepped forward. The skepticism that had defined his earlier stance was gone, replaced by something closer to respect. "Your system has exceeded our expectations," he said to Smith. "The question now is how quickly it can be put into production." "Where?" Smith did not smile. He understood what success really meant. The aircraft had won its argument in the air. Now it had to win it on the ground. Production realities would not be kind. Precision manufacturing at scale was difficult. Training pilots to trust an unfamiliar system would take time. Maintenance crews would need new procedures. But the most important barrier had fallen. The idea was no longer theoretical. It was proven. The laughter that had followed the proposal had no place left to stand. As engineers gathered around the aircraft, examining the propeller assembly with new eyes, the meaning of the flight became clear. This was not just a solution to the Spitfire's problem. It was a lesson. Speed alone was not enough. Power alone was dangerous. True control came from understanding how forces interacted, not from trying to overpower them. The contra-rotating propeller had revealed something few engineers had fully grasped. High-performance aircraft were no longer limited by engines. They were limited by how intelligently power was managed. That realization would not remain confined to one aircraft. It would shape designs that followed. Smith stood beside the Spitfire as the hangar slowly emptied. The machine that had nearly ended his career now represented its defining achievement. But he did not celebrate. Because he knew the truth. This success would not be remembered for the gears, the blades, or the numbers. It would be remembered for a moment when speed stopped being an enemy and became an ally. And from that moment on, fighter aircraft would never be designed the same way again. The victory in the air did not end the argument. It changed it. In the days that followed the second test flight, reports circulated through offices that had once dismissed the idea outright. Not summaries, not opinions, numbers. Speeds held without vibration, climb rates restored. Handling improved where it should have degraded. For the first time since the Griffin engine had been introduced, the Spitfire was no longer fighting itself. That mattered more than speed alone, because the war in the air was not won by peak performance. It was won by what pilots could actually use. Production planners now faced a different problem. Not whether the contra-rotating system worked, but whether Britain could afford to build it at scale. The answer was complicated. The propeller system demanded precision machining beyond standard fighter production. Gearboxes had to be cut and assembled with exceptional care. Blades had to be balanced far tighter than anything frontline crews were used to handling. This was not something that could be rushed. As a result, the contra-rotating propeller never became universal across all Spitfire variants. It appeared where its advantages mattered most: high power, late war aircraft, pushing the limits of speed and control. But its impact went beyond numbers on a production chart. The flight at Boscombe Down changed how engineers thought about power. For years, aircraft design had followed a simple pattern: more engine, more speed, more advantage. The Griffin Spitfire broke that assumption. It demonstrated that raw power could become a liability if the aircraft could not manage it. That beyond a certain point, speed without control was not progress, it was danger. The contra-rotating propeller didn't merely fix a problem, it revealed one. Torque had always existed. Engineers had simply accepted it as something pilots would fight. Smith's design proved that this acceptance was a mistake. The aircraft did not need stronger pilots. It needed better balance. That lesson echoed far beyond Britain. Other nations were encountering similar limits as engines grew more powerful. High-performance fighters across Europe and the Pacific struggled with control at speed. Designers faced the same question Smith had confronted: how to harness power without letting it tear the aircraft apart. Some adopted contra-rotating systems. Others sought different solutions. But none could ignore the underlying truth anymore. The age of simply adding horsepower was ending. In the months that followed, Allied air power continued to grow: faster aircraft, better climb rates, improved high-altitude performance. And while the contra-rotating Spitfire was not solely responsible for that dominance, it played a role in redefining what was possible. Not by being flashy, not by rewriting doctrine, but by quietly removing a limit that many had assumed could not be removed. For Joseph Smith, the outcome was quieter than the struggle that preceded it. There was no public celebration, no dramatic announcement. The work simply moved forward. Smith returned to design problems that demanded the same discipline he had always brought to them, finding solutions where others saw only trade-offs. But the label that had followed his proposal did not survive. The idea, once dismissed as stupid, had proven something uncomfortable. That ridicule often comes not from certainty, but from habit. The people who laughed at the design were not incompetent. They were experienced. They were cautious. And in war, caution usually saves lives. But sometimes, caution protects assumptions that no longer hold. The contra-rotating propeller forced that realization. It showed that complexity, when understood and controlled, was not weakness. It could be strength. More importantly, it demonstrated that the most dangerous problems in engineering are often the ones everyone believes they already understand. Torque had been known for decades. Its effects were well documented, and yet its consequences had been underestimated, until speed pushed aircraft into territory where old rules stopped working. The Spitfire did not win the war alone. No aircraft ever does. But it carried the war into a new phase, one where mastery of power mattered more than power itself. The sky remembered that lesson. Long after the last contra-rotating propeller was shut down, designers continued to wrestle with the same balance. Jets would soon replace propellers, introducing new challenges, new limits, new failures. But the principle endured. Performance is not about how much force you can generate. It is about how precisely you can control it. That is what the Spitfire's most controversial modification ultimately proved. Not that speed was everything, but that understanding was. And in a war defined by machines pushed to their extremes, that understanding quietly shifted the balance in the air. The aircraft that had once become too fast for its own pilots had finally learned how to fly at the speed the war demanded. Not by overpowering the problem, but by respecting it.